Thanks for the presentation. I am, as I said, Javier Vazquez Corral. I am from both the Autónoma University of Barcelona and the Computer Vision Center. And I am going to present our CVPR paper this year on the art of deception, color visual illusions, and diffusion models. So why we are studying this? So at the end, the motivation comes from what is traditional in vision science, the empirical or statistical model of vision that says that when humans or any type of animals are looking at reflectance in a multiluminant environment, they guess what's the colors there by two things, by what they are seeing and with all the knowledge they have gathered in his lifetime through goal-directed behavior. At the end, this is extremely similar to what we are doing with all these models. We are giving millions and millions of images, which will be our previous knowledge, and we are trying to address what's happening. So let's see if there are any possible parallelisms, if we can find any relation between them. Of course, I should start telling what are visual illusions. I am from Barcelona, born and raised. So what is the most traditional thing you can show in Barcelona? It's the Sagrada Familia. So even if you don't believe, so if I take this Sagrada Familia, I passed it in this yellow or blue backgrounds, and then I use the other color as stripes in front of the image. In one case, you perceive this Sagrada Familia as purple, and in the other case, you will feel it like orange. So this is a visual illusion. Visual illusion is where what the physical measure means, because if you point a photometer here, these have exactly the same values, and what our brain says are different. And these are key to understanding vision, our brain, because learning for errors is sometimes the best way to understand what is happening. Of course, this is just a color illusion. There are many types of illusion. There are distant illusions, so these both arrows are the same. We have some kind of straight lines looking like not parallel anymore. There are some motion illusions where we can see motion even if they are static things, but we are mostly focused in color and brightness illusions. I am mostly a computational color person, so we will focus on these illusions. Of course, we need to say we should be careful. We are analyzing different systems. They work differently, so be careful on that. And that's already few studies, some of from ours and from other people that are already looking at them, and they are already starting some different conclusions. Having said that, what we see is we have two paths. There is a path saying, okay, what do traditional visual illusions fool ANNs, in this case today diffusion models, and of course we will have a second path that, okay, that's one, and the second path will be the opposite. Can I make with an ANN a visual illusion that will fool a human? So we are going to go, in this talk, we are going to look at both. On the first one, do human illusions fool ANNs? So of course there is some works previously work at this. Probably the first work was our paper in CVPR 2019, where we looked at this for end-to-end models, autoencoders, but there has been lots of different works also for illusory motion and so on. So we are not the first in doing it, but we are the first in to get into this step of diffusion models. And what we found? So everything comes from this observation. So we take the DDIM inversion, and we start the forward process with the traditional white illusion. And we start adding the noise following the DDIM injection equation. And of course, at the beginning, we know it is physics. Both patches are equal. But as we start to add steps on DDI inversion, we reach a point where the image is starting to be as we expect. So the model is outputting a darker region in the left and a brighter region in the right, as our perception says. Of course, we can see that what we are doing is what is expected on the DDIM process. If we look at the histogram of the latent space, we are Gaussianizing the distribution. Of course, you can say, oh, this is just lag. You just try the white color illusion. Maybe it's just something that appears in one and does not happen, but that's not the case. If we do the same in different illusions, we just do between 5 and 20 DDIM steps, we get the effect. For example, in the famous Adelson checkerboard, so A and B, even if you don't believe they have exactly the same gray value, as you can see here, and by running the DDIM inversion, you are getting what the perception says it should be. Also with the cube illusion, again, B and A are exactly the same color, it's just the context that change. And even a very traditional, which is color constancy. If we take these three different images and we run it through DDIM inversion, we can see how this red color, that as humans we know that it's going to be the same, gets much, much closer. There are even more illusions where we can prove it, and also some illusions that happen on real image, we can see that we are also able to found them. Or this is a very challenging one, so you can see that it's exactly the same circle all the time, but the model is able to give the feeling, and nicely it gets very much to the color we are perceiving. So okay, this is very nice, but how you measure that? So to measure that, luckily we already have a few data sets. We have the brightness illusion data set where we have 5 types of different illusions on grayscale with binary mass indicating if there is an illusion or not. And we also have a color categories on 3 other visual illusion, visual question answering data sets. Second question is how you do measure. The traditional way is you look at the places where it should be an illusion and you measure by comparing the values on those patches if it's an illusion or not. It's no more than that. So having said that, we can look and we can see how in both data sets, these are very traditional models, this Odok and C1, we can see that we are much better than them and we are better than the other ways of addressing visual illusions with autoencoders networks in both datasets. Also, very importantly, we can clearly see that the variational autoencoder is not the part that it's doing this. It's really the DDIM. So it's really happening because of the DDIM process, of this inversion process. So now, having known that, we can answer the second question, that it's okay. It seems that this DDIM is giving the correct perception. Can we use it to create visual illusions that fool humans? Again, there are different works that already try to generate visual illusions. We did one some years ago, but there was also the Visual Anagrams famous paper on CVPR 2024. So they are different methods that have tried to do this. And of course, we are able to do it, and how we do it. So the idea is, okay, let's take this replication capability that we have seen on the forward pass, and let's try to use it to optimize the noisy latent representation, the representation in the backward pass. Of course, as we are just optimizing the noisy latent, this is a training free. And the idea is very easy. So we get any step and we get the noise and the targets. We pass the targets and we run it through the unit and we compute if the perceptual feeling that we want to own, it's addressed or not. We sum up this perceptual with a similarity term of also of the loss, so the patches embed very well with the content, and we compute through this loss the update of the noisy latent. So if we look at this, we can see that we just need to provide then a prompt, a set of regions, and a visual perception condition for each region. That's all we need to give to create an image that generates a visual illusion. So for example, we can have things like this. So we can ask for a portrait of a beautiful girl, beautiful eyes, princess detail and intricate, elegant, ornate luxury. We want to say we want this color and we want a perception where in the left it's lighter than on the right. So the model is able to generate an image where both of these patches are exactly this color, but the feeling you have is that this is lighter than this. So we have here some of their examples with the text. So for example, here we do an avocado chair with a Van Gogh style, and we tell that these two patches should be of this green, and this one should be darker than this. And we are able to generate that. So we have plenty other visual illusions, and interestingly, it's not only about color, we can do the same with textures. Also, we can embed textures with visual illusions in the same way. So just to wrap it up, some take-home message. So the first one to know is that artificial neural networks, even diffusion models nowadays, they do exhibit similarities with human perception at many levels. Of course, there are differences between these ANNs and human visions, and most of the properties cannot be directly extrapolated, but the similarities between both, they can offer insights on how it works visual information processing and help developing optimal representation theories. So yes, I want to finish thanking the Spanish Ministry for the project that allows us to do this, and if you have any question, I will be happy to answer.
Hi, thanks. I really love visual illusions. That's really cool. I wanted to ask if you experimented at all with non-color based sort of visual illusions, right? So stuff like non-Euclidean imagery, and see how that works in terms of the visual imagery, right?
We did not. So I am a computational color low-level vision researcher, low-level computer vision researcher. So my specialty is color and brightness, and we focus on those type of visual illusions. There are some other works that have been looking at illusory and motion visual illusions. Some work by a group in Japan, mostly, but we have not looked at that, unfortunately.
Okay. No. Yeah. Thanks. Okay.
Is there some explanation for why these models, can have these illusions? What is the reason? Is it like a data or like?
For me, it's very similar to the most known theory of why they happen in our brain is efficient coding. So at the end, our brain has lots of information and needs to make it efficient. So what it does, it just make it efficient by following the statistics that most image will accomplish. What happens with visual illusions? They don't have that type of statistics. They are kind of out of the normal statistics. So my guess is something similar is happening when we are doing the diffusion process. We are trying to Gaussianize the distribution. So probably those visual illusions are really much more difficult to Gaussianize. And it's kind also of this efficient coding problem, but on the network side. So that's my bigger guess. But it comes from this connection on how already efficient coding works on the brain.
So nothing to do with like how colors represented on computers or anything like that. Like it's about.
I don't think so, because I think if you change the color space, you will still have them. Okay. If you go to LAB color space or any perceptually based open-end space, you will still have the illusions.
Okay. Thank you.
Yeah. There's another question. That answered my question.
Okay.
We have like one question, if any.
If possible, for example, the Sagrada Familia.
Yes.
Have you found ways to control what color it should appear to the human eyes? If I wanted to make it appear green, do you know which bars to put?
So there are works doing that. We did a work related similar to that when trying to. So it's a different topic, but it's based on the same principle. So if you when you look at a movie at a cinema or in a mobile phone, you perceive it very, very differently. a way of addressing how you need to change one image to make it similar to the other is by studying these shower rings, these illusions where there are rings with a color in the middle. Because as you will perceive that differently at different distances or a different size of a screen, you will be able to somehow formalize that to do that change on your smaller screen. So we have been looking at that, not directly, but as a proxy for other problems.
Yeah, thanks, David.